Hi, I'm Uma from Succinct Labs, and yeah, I'll be giving a quick talk on what we're doing with Succinct verification of consensus. So I'll skip over like the parts you guys already know about. Like basically, there's been a lot of L1s and L2s, and as there's been more L1s and L2s, interoperability and cross-chain communication has become really important, and it's really critical infrastructure. In today's world, all L1 bridges are basically built with multisigs or off-chain oracles, and so they're not very decentralized, they're not permissionless, they're censorable, and then also empirically they get hacked a lot, which is really bad for the whole space and really bad for users. And so what we did over the summer and was generously grant funded by Gnosis was thinking about kind of like how do we build a better bridge architecture and better bridge design. So what we came up with in collaboration with the people at Gnosis and Gnosis Chain is basically bridge security should be based on the same mechanism validators already use to agree on state. So there's already a consensus protocol that everyone uses to agree on the state of a chain. And so what if we could just verify consensus of a source chain in the execution layer of a target chain? That's a high-level idea. This is what things like IBC from the Cosmos ecosystem is based off of running light clients in the execution layer of a chain for another chain to have like trust minimized interoperability. And so, yeah, what this looks like at a high level is you have Ethereum, which during the course of its like operation is producing a bunch of block headers and signatures from validators. And then you would have an Ethereum consensus verification smart contract that lives on Gnosis Chain that verifies Ethereum consensus and then has access to Ethereum state roots. And once you have Ethereum state roots, you can verify any piece of Ethereum state or any activity going on Ethereum in the smart contract. So you could build like a token bridge, but you can also build a lot of other like cross-chain apps. And so, yeah, as I mentioned, like once you have these headers, then you have these state roots, and you can have storage proofs that have trust minimized verification of blockchain state, which is really great. But implementing consensus is verifying consensus is really tough. So for Ethereum, there's like 400,000 validators. You have to keep track of the whole set of validators. You have to verify these BLS signatures. That's really expensive because there's no precompiles on the EVM. And so the Ethereum protocol has this sync committee, which is a random subset of 512 validators that's rotated every 27 hours. Validators sign every block header. And basically, if we can verify this sync committee's consensus, which is just 512 validators, we can kind of get like a weaker security guarantee than verifying full consensus itself, but it's still pretty good for running a light client in a smart contract. So that's what we did. And as you guys know, Gnosis Chain is like an Ethereum chain as well, right? So it uses Ethereum, or it will use Ethereum proof of stake to secure the chain. Hopefully, whenever the merge happens, I'm not sure when that's happening. But yeah, when that happens, then if we have this algorithm to verify the sync committee's consensus, then we can have a two-way bridge between Ethereum and Gnosis Chain that runs light clients for either chain on the other. Okay, this is actually still too expensive to verify without just natively in Solidity or in a smart contract. And so, yeah, there's a bunch of details here that I won't go into. And so the key idea that we had was like, okay, what if we can use zero-knowledge, the succinctness property of ZK snarks, and instead of verifying validator signatures on-chain, you can just move the expensive parts of the computation off-chain. You put it in a snark, and then you simply verify the proof on-chain. So similar to how like ZK EVM teams are scaling execution with snarks, we're scaling verification of consensus with snarks, which is what we call proof of consensus. So the idea of like proof of consensus, it's like a short way to say we're using ZK snarks to generate a validity proof of the state of a chain according to its consensus protocol. Okay, yeah, so we implemented that. And there's a bunch of details on like we had to build a lot of circuits in CirCom. We had many constraints. Like it was a painful process generally because you have to verify these signatures. You have to do out-of-field arithmetic. You also have to verify that the signatures are coming from like the correct set of validators. So you have to do a bunch of inclusion proofs, and you have to deal with like Ethereum's SSZ inclusion, which is like not very snark friendly. And then we had some tricks we did to reduce gas costs of storing public keys on-chain. So basically, like snarks have public and private inputs, and we were able to remove having the public keys as public inputs into the snark, which would require posting all the public keys on-chain, and instead putting them as private inputs into the snark, and then you can just keep a commitment to the public keys in the snark, and that's much cheaper, like from a storage cost perspective. And so we had to do like some tricks and map like a snark unfriendly commitment to a snark friendly commitment that I won't go into for the sake of this talk. But the bottom line was these tricks helped us save like 70 million constraints in our header verification snark. So that's actually quite significant. So it helps us save in like proof generation time and like proof generation memory costs and things like that, which is really important. Okay, and then for some benchmarks, so what we did is we implemented this. We have a snark that verifies the sync committee signature, and then we have another snark that allows you to like rotate the sync committee basically. So we have two circuits. As you can see, they're pretty large. One has around 70 million constraints. Another one has 20 million constraints. Thankfully, the proving time is not that bad. They're around like 4 minutes each. So it's like very practically feasible today. And then we have a demo bridge that uses this, where you don't go to this on mobile. It doesn't work on mobile. It's really bad. But you can use this, and we have this up and running, and you can basically bridge from like go early to Gnosis, and you have like some fake tokens that you can like transfer over. And we have a light client running on Gnosis Chain that has go early block headers. So we have like an operator running that has the block headers, and then we use those block headers to basically prove that you deposited into a bridge contract, and then that lets you mint tokens on the other side. So that's kind of like a proof of concept of this working. Yeah, this just shows it working. You can see like the light client updates, and then a transaction going through. And yeah, I think zooming out, kind of like pros and cons of proof-based bridges. So like one huge pro is that it has like a much better trust model. You're not trusting a multi-sig. And so, you know, its trust model is probably like one of the best you can do. You're just trusting like the consensus of the source chain. It's more censorship resistant because theoretically anyone can look at Ethereum's data, generate a proof, and then submit an update to the other chain. And it's much more decentralized because, again, anyone can generate these proofs and submit updates. Some of the cons are it has like higher gas costs because we have to actually submit updates. It's higher latency because we actually have to generate these proofs. Although with newer generation proving systems, probably the proving time can go down a lot. And then technically, it's like just quite difficult because you have to implement new snarks for every different consensus algorithm. And so it requires just like a lot of engineering effort. Cool. And then, yeah, I guess like zooming out a bit in terms of like what we want to do. So our goal is like we want to become this trust minimize interoperability layer for Ethereum and other decentralized protocols. And we want to like do this same thing. We currently have built a proof of consensus for Ethereum, but we want to do it for other chains. And basically, we want to power like all cross-chain communication through this primitive. Yeah, and I think we have a few other things that we also want to do. But yeah, also a huge shout out to Gnosis to like funding and supporting this work from the beginning. And yeah, we're working really closely with Gnosis Chain to improve, to have their bridge design use a proof-based design like this. And yeah, they've been super great collaborators. And yeah, like gave us the idea to begin with. So